Okay, so here we have a good example that covers quite a few topics. So we have a composite beam, and it has two wooden boards that each have a width of 3 inches and a depth of 12 inches, and they are bolted to the sides of a steel plate with a thickness of 0.5 inches, and it also has a depth of 12 inches. So that's nice. All three of our parts have the same depth. Okay, and that's shown in the figure. So we have a modulus of elasticity of the wood of 1800 KSI, and for the steel we have a modulus of elasticity of 30,000 KSI. We have a simply supported beam that spans 24 feet here, and it carries this uniformly distributed load of W. And then, so for part A, we're supposed to find the maximum bending stresses produced in the wooden boards and the steel plate if W equals 400 pounds per feet. So sigma max equals negative my over I. So we need to find M. And then we'll find Y, and then we'll find I. But to find M, we get to do a shear moment diagram. So first thing we have to do is solve for the reactions. And then we can draw our shear moment diagram. So our free body diagram of this beam would have a vertical reaction at A. A is a pin, but there's nothing going on in the x direction, so we'll leave the x support off. Then we have 400. This is 400 pounds per foot. We're going to turn that into a point load that's going to act right in the middle of the distributed load, which is right in the middle of the beam. And that is going to be 400 pounds per foot. It acts over 12 feet. So times 12 feet, and we get that this point load is 4,800 pounds. And then we have a reaction at B. Okay, so if we sum the moments about A, that'll equal 0. And so we'll get, this isn't B, this is actually D. RD. We get RD times the whole length of 24 feet. That's a positive moment around A minus 4,800 pounds times that acts halfway across the beam, so that's 12 feet. So we have times 12 feet. Solving for RD, we get that it equals 2,400 pounds, which is half of this load. We could recognize that, or we could just say the sum of the forces in the y equals 0 equals RA minus 4,800 pounds, that's our point load, plus RD, which we found to be 2,400 pounds. So then RA also equals 2,400 pounds. So then we draw our shear diagram. We can draw that here. At A, we jump up 2,400 pounds. Nothing happens as we walk across the beam. Once we get to the distributed load, now we're going to drop down 400 pounds per feet for a total drop of 4,800 pounds. So we're at 2,400 pounds. I'm going to drop 4,800 pounds, so we'll be at negative 2,400 pounds. Then, as we continue to walk across the beam, nothing happens until we get to RD, which is also a positive 2,400 pounds, so we close. So that's good. Shear diagram went well. Now we need to make a point that V equals 0 at X equals 12 feet. And we know that just from symmetry, that this is going to cross at 12 feet. So, and that will be a maximum moment. So now we can draw the moment diagram. This is the shear diagram. Continue our lines down. This is where the max will be. Okay, and so now we have M. So we have a shear area in here of AV1. We could call this area of shear 2. We could call this area of shear 3. And we could call this area of shear 4. So we can calculate those. And looking at that, we can see that area of shear 1 equals a negative area of shear 4. And that equals 2,400 pounds times 6 feet. So this area equals 14,400 pound-feet. Then we can see that we have AV2 and AV3. So the area of the second shear area equals the negative of the third shear area, and that equals 1/2 of 2,400 pounds times, this is 6 feet again, so times 6 feet. And we get that this shear area equals 7,200 pound-feet. These shear areas are our change in moment. So we know that when we get to this first dotted line, we have a flat line here on our shear diagram, so we are going to have a linearly sloped line starting at 0 and going up to 14,000. I'll make this red so you can see it better. Linearly sloped line starting at 0. It's positive area, so it's a positive slope. And we get to this point, and it is 14,400 pound-feet. Okay, so that's the first area. Then we have to go up by the area, the second area. It's still positive. Now we have a sloping downward shear diagram, which means that the slope of our moment diagram is going to be curved. It's going to have a steeper slope at the beginning and a flatter slope at the end. And it's going to hit a maximum where the slope will equal 0 when we get to this point. So we have to go up by an additional 7,200 feet, putting us at, so we start steeper, then we're going to get flatter, and we get to 21,600 pound-feet. All right, and then our third shear area was just the opposite of our second shear area. So now we have a negative shear area, so our slope is going to be opposite. So we go down back to 14,400 pound-feet. And then our last shear area was this AV4, which is a straight line. So we'll have a linear sloped line bringing us back down to 0. The most important part of this is the M max. That's why we had to do all of that. So we get an M max equal to 21,600 pound-feet. Okay, so we're supposed to find sigma max. So now we have M max. So we have the M, now we need to find the Y and the I. The trick here is that this has two materials. We have wood and steel. So we are going to need to transform this section. So sigma max equals a negative my over I. We need to transform section. And what we're going to do here is we are going to turn the steel into wood. Okay, so we need to calculate N. And we're going to stick with N equals the large elastic modulus, so that would be of the steel, over the elastic modulus of the wood, which would be E small. So this equals 30,000, these values were given, KSI, all over 1,800 KSI. And we get an N value of 16.67. Now we need to increase the width of steel. We never increase the height. So now we have that the new thickness of steel transformed is going to be equal to n times the original thickness. And so the n is 16.67. The original thickness was 0.5 inches. And we get the thickness of steel transformed equals 8.33 inches. So now we had this original cross section. Now we're going to treat it as a transformed cross section. So we're going to draw that. The height stays the same for all parts. So we still have a height of 12. The wood stays the same at 3 inches. So here's the first wood section. Then we have this steel section that was 0.5 inches, and now it's going to be 8.33 inches. So that's going to look something like that. And then we have our second wood section. So we have 3 inches here, 8.33 inches here, and we have 3 inches here. We have a rectangle, so our neutral axis goes right through the middle. This is all, the whole depth was 12 inches, making our y bar the distance from the bottom to the neutral axis. Y bar equals 6 inches, just halfway up, because it's a rectangle. Now, the moment of inertia is a little easier here because we just have a rectangle. So we can do I equals BH cubed over 12. And this equals, our base is now 3 plus 8.33 plus 3 times our height is 12, and we cube that all over 12, and we get I equals 2,064 inches to the 4th. Okay, so now we look at our equation again to calculate sigma max. All we needed was m, y, and I, so we have all of that. So we have to calculate sigma max both for the wood and the steel, and then see which controls. So we'll start with the wood. We did not transform the wood, so sigma max of the wood equals negative my over I. Since it's a rectangle, that means that y top equals y bottom. So sigma max will be positive or negative. So sigma max at the top top equals the negative of sigma max at the bottom. Okay, so we can plug in what we know. Sigma max of the wood equals our moment that we calculated was 21,600 pound-feet. We need to change that to inches. Our Y is 6 inches. And we divide all of that by I, which is this 2,064 inches to the fourth. And we get a sigma max of the wood equal to a positive or a negative 753.5 psi. First answer. Now we look at the steel and we see which one controls. The steel is what we transformed. We made, this is wood, steel, and wood. This is N times T, so we have to multiply our sigma max of the steel equals, this is also going to be positive or negative, so I'm just going to leave off the negative sign, N times my over I. So don't forget the N. Sigma max of the steel, our N was 16.67. Our M was 21,600 pound-feet times 12 inches per foot times our Y of 6 inches all over our I of 2,064 inches to the fourth. And we get a sigma max of the steel equals a plus or a minus of 12,558 psi. So I guess this one we didn't really have to, they just wanted us to find what sigma max is. So that would be, it would, so we would look, that would be the 753 would control. Okay, that was part A, no big deal. Now we have to do part B. So assume that the allowable bending stress in the wood and steel are, so we have a sigma allow of wood is 12,000 psi and a sigma allow of steel of 24,000 psi. And we're supposed to find the magnitude of what would W be in this case. Okay, so this is, so we are going to start part B here. We have sigma allow of the wood equals 1200 psi. We have sigma allow of the steel equals 24,000 psi, and we're supposed to find what does that distributed load here, what does that equal using these two limit states. So if we look at sigma max for the wood equals a plus or minus my over I. We don't need an n here. So we plug in 1200 psi equals m times y stays the same at 6 inches, I stays the same at 2064 inches to the fourth, and we get a moment from the wood equal to 412,800 pound inches. So that's the maximum moment that we can have staying within this allowable stress. So now we look at the steel, and sigma max of the steel, we have to multiply this times n again. So we have n times the moment of the steel times y, because we're still using our I of the transform section. So now we can plug in 24,000 psi equals 16.67, that's our n, the moment of the steel times 6 inches all over 2064 inches to the fourth. And we get that the moment of the steel equals 495,360 pound inches. So this is the allowable, this moment, we can't put this moment into this equation and stay under 1200. So this moment controls. We take the lesser. Now, the hard part is solving for W. So we know M max, and we know it occurs at x equals 12 feet on the beam. So, cut at x equals 12 feet and get a moment equation in terms of W, because that's what we're looking for. Okay, so might just do this quick. We're gonna grab this and paste it here. So what I'm doing here is I'm going to cut this right where M is a maximum, and that is 12 feet. So I have to solve for the reactions with W as a variable. So I have RA. I'm treating this as just W times 12 feet. And then I have RD. So if I sum moments about D again, it equals a positive W times 12 feet times another 12 feet from, this is 12 feet. So we have times 12 feet. All minus RA times 24 feet, the length of the beam. So I get RA equals 6 feet times this W we're looking for. I only need RA because I'm going to cut this from the right side. So I have my cut. Now I have RA, which equals 6W. Now this distributed load, instead of acting over 12 feet, I'm at 12 feet. Total is the length of my beam. Now I cut it. So when I cut it, I end up with a negative shear, a positive moment internally. This is acting over 6 feet. So if I draw this as a point load, I have W times 6. And what I'm going to do is sum the moments about the cut. That'll be 0. The V won't be in the equation because it's on the cut, so I'll have this equals a positive M plus this W times 6 feet and it is 3 feet away. And then I have to subtract RA, which is 6 feet times W. Oh yeah, we can put that times 12 feet. So I get that M equals 54 feet squared times W. Now I just have to plug in my controlling M, which was this, and solve for W. So I have 412,800 pound-inches. This is in feet, so I'm going to multiply this times 1 foot per 12 inches. So turn it into pound feet, and that is going to equal 54 feet squared times W. I solve for W, and I get 637 pounds per foot is the maximum distributed load. So that would be here. This would be 637 pounds per foot now. And that's to stay within these two controlling sigmas. All right, I hope that